joining me. Today I want us to look at nuclear energy. Remember, in our previous video, you will see the link in the description down below. We discussed the concept of binding energy, and we said that yes, for that of binding energy, it is the energy that holds the nucleons together, and the same energy that is holding the nucleons together, we still separate them. Today I want us to look at this nuclear energy. Nuclear energy is nothing but the energy that is produced from the nucleus of an atom. Or we can still say that yes, nuclear energy is that energy that is produced during either nuclear fusion or nuclear fission, especially when used to generate electricity. So that energy, and of course it is enormous energy, that energy produced, or that heat produced in that process, is what we refer to as nuclear energy. Now, there are two types of nuclear energy. Now, in terms of nuclear energy types, there are basically two types of nuclear energy. One, we have the nuclear fusion, nuclear fission, and the second one, we have the nuclear fission. So we'll look at this one after the other. Now, for nuclear fission, we'll look at it first. Nuclear fission is nothing but the splitting of a heavier nuclide into two or more approximate equal nucleus, and the release of about three neutrons or more, and huge of energy, a huge amount of energy, by the process of neutron bombardment. And of course, by that neutron bombardment, we can split this heavy nucleus only with the help of a fast-moving particle like a neutron. So once we bombard a heavy element, for example, uranium 236 minus 148, whatever we have, remember there is 3 here also, so we can now have 236 minus 148, which will give us 88. Now this 88, we subtract 5, we subtract 3. If we subtract 3 from here, we now have 85. So in other words, this plus this will give us 236, which is here. Now on this side, already this is 3 times 0 is 0. Now I have 57 here already. So 92 here minus this. 92 minus 57. The remaining will now be this, and of course it corresponds with the atomic number of barium. And this is our energy released. Remember, from our definition, we say that it is a splitting of a heavy nuclide into two or more approximate equal nuclide with release of 3 neutrons by this neutron bombardment. So, having done this, remember this is a fissile neutron. This fissile neutron produced, this SS neutron produced, care must be taken so that they don't cause further fission process if they hit other materials. So in other words, in order to carry out nuclear fission, it must be carried out in a nuclear reactor. In our next video, we'll look at what nuclear reactor look like and the component parts of a nuclear reactor. So, in other words, in conclusion, we have these 3 neutrons produced. They must be guarded so that they don't cause further fission process. Of course, if they cause further fission process, it might lead to what we call chain reaction. And of course, chain reaction can cause explosion. For example, assuming we have this element X, and then during nuclear fission, 3 neutrons are produced. This is a neutron here, this is a neutron here, this is a neutron here. Now, if this one neutron hits another neutron, and of course 3 neutrons will be produced. If this one hits another element, 3 more neutrons will be produced. So in other words, I just first the second fission process. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, assuming this other one continues to hit other elements, causing them to split. In other words, it can lead to chain reaction. So let us look at nuclear fusion. Now, by nuclear fusion, we mean that nuclear fusion is just the process of bringing 2 very lighter nuclei together in order to form a heavier nucleus. And of course, it is that this process is achievable under very high temperature conditions. For example, we can have this nuclear fusion. Now we can have proton plus deuterium, proton plus tritium. So these are very lighter nuclei. So it can now give us helium. It can give us helium. Of course, this plus this is 4, which is 4 here. This and this will give us 2 plus energy produced. We can also have a process whereby deuterium can maybe fuse, or deuterium combining with the tritium to give us, and of course this plus this is 5, and if we have 5 here, we'll have 2 here, plus neutron, 1 neutron. This neutron gives us 0 here, and then this one gives us 1 here, and 0 here, plus energy produced. So this process, and more, there are other things that can see, neutron can still fuse with another element to give us a higher element. So these 2 are lighter elements, while this one, especially this, is a heavier element plus this. Now, if we compare fission and fusion, the difference between the 2 is that yes, this for fusion is human friendly, environmental friendly, whereas this one is not environmental friendly because it has to do with splitting of element, and especially with these 3 neutrons. Whereas for this one is friendly, human friendly. But the only difference between the 2 is that yes, this one occur at a very high temperature, while this one can be achieved at a low temperature, at any considerable temperature. Now this one, the materials that will withstand this high temperature most times are difficult to come by. Whereas for this one, the materials are cheaply available. So in other words, this one is human friendly, yet we prefer this. The reason why we go for this one most of the time is because of availability of raw materials. These one, the raw materials are very, very available. This one, this is what happens in the sun. Of course, this gives us that enormous energy that is produced in the sun. Now, let us look at this energy produced. So, we now say that, yes, note, energy released, this energy that is released here, energy released is called nuclear energy. Now, and this nuclear energy, we can calculate this value of this nuclear energy using what we call Einstein's equation. Now, this Einstein's equation can be written as E is equal to delta mc squared. Where delta m, on most times most people use mc squared, but it's better to use delta m because most times there will be change in masses. Now, I will tell us this change in masses. While c here is the speed of electromagnetic wave. Most times is the value of c is 3 times 10 raised to the power 8 meters per second, which is the speed of electromagnetic wave. Okay, now let us take one or two questions to buttress it. However, before we do that, if we assuming this one, we want to calculate this value of energy released here, maybe in this one or in this one. All we need to do is we can write that equation. If we write that equation, giving us deuterium and tritium, giving rise to helium 2 and neutron 0 plus energy. All we need to do is, this one is called a reactant. This side is the reactant. While this one here is the product. This one is the product. So, reactant minus the product plus this. So if we make E the subject now, this one, remember this is a quality sign in mathematics. So if we make E the subject now, E will now give us, of course this one will go over here. E will give us reactant minus product. So if we now include, because for this one you'll be given mass of this, all these elements you'll be given their masses. So if you are given the masses, you can now say mass of reactant minus mass of the product. Mass of reactant minus mass of the product will give us this. Now most times, if it is given in atomic mass units, you'll be given the value of atomic mass units. But if the value of atomic mass unit U is not given, then they will give us C. If they give us C, all we need to do is, once we get this mass difference, mass of this minus mass of this, and then we'll multiply it by the value of speed of light, and that will give us the energy release. So let us take one or two calculations to buttress what you have just taught. Okay, we look at the first question. The first question here says, a nuclear reaction is given by the equation. We have the equation there, deuterium plus tritium, giving rise to helium and neutron plus energy. And they say, calculate the quantity of energy released. These are the masses given to us. Mass of deuterium, tritium, helium, neutron, and then we'll have the value of speed of electromagnetic wave. Now, all we need to do is solution. By that, we have the reactant. We have the reactant on this side and the product on this side. So all we need to do, just move straight, make E the subject of the formula. Now, E will give us that if we make it the subject, we have E is equal to the reactant 2,1 plus 3,1. We'll have it here, minus the product. Just send this one that side. The product is helium 4,2 plus neutron this. Okay. Slot in the values. So energy released will not give us, for deuterium, we put this 3.345 times 10 raised to the power minus 27 plus this, which is this 5.008 times 10 raised to the power minus 27. We retain this. Put our minus. I'll write it down here. If we write it down here, the reactant, the product will now give us minus 6.647 times 10 raised to the power minus 27 plus that of a neutron, which is 1.675 times 10 raised to the power minus 27. Okay. Now, at this point, remember from the law of indices, when we have a equation of this nature, add the base, those bases, add the bases together, and then since the index numbers are the same, just pick one of them. So which will now give us, for add the basis, we now have that E is equal to 3.345 plus 5.008 times 10 raised to power minus 27. We are done with this one. Minus this other one, 6.647 plus 1.675 times 10 raised to power minus 27 on this side. Now, at this point, we can now bring in our calculator. So, if we say 3.345 plus this, it will give us 3.345 plus 5.008, which will give us 8.353 times 10 raised to the power minus 27 minus this side 6.647 plus 1.675 will give us 8.322 times 10 raised to the power minus 27. So we now have a simple value now. Still, their index numbers are the same. Because we are subtracting, we subtract the basis and then pick the index number. So the basis now will give us 8.353 minus 8.322. 8.353 minus 8.322 will give us that E is 0.031 at this point now times 10 raised to the power minus 27. We now have a single value, kg. So this is our mass, E. Now remember that but E is equal to delta M C squared. This is our delta M. So all we need to do is to multiply by C squared. And of course, this is the value of C. So if we multiply this, we now have that at the end of the C is 0.031 times 10 raised to the power minus 27 times C, 3 times 10 raised to the power 8. We will now have that E is equal to, if we multiply this, remember the law of indices, you multiply the bases. Remember there is a square here, please. There's a square here. So which will give us 0.31 times 10 raised to the power minus 27 times, if you square this, law of indices says square this and multiply the base, the index by 2. If you square the base will give us 9 times 10 raised to the power, this time it is 16. Okay, we now have that E is equal to, at this point, multiply this and this. 0.031 times 9 will give us 0.279 times, now multiply the index numbers now. The index numbers are minus 27 plus 16. It will give us minus 11. So it was minus 11. Therefore, times 10 raised to the power minus 11. This is not in standard form, so we'll put it in standard form. Therefore, E is, we'll push this down here, which will give us 2.79 times 10 raised to the power minus 12 joules. And this is the final answer. Second question says, deuterium and tritium are fused to form a helium nucleus according to this equation. And they said, calculate the value of energy released in joules. In joules. So we have this as in joules. Now this one is given in terms of mass number. So the mass of these elements, deuterium is going to be this, mass of this is going to be this, and all the rest of this. Of course, this is similar to the former one. Now, the difference between this and the former one, you are giving these masses in terms of atomic mass units, whereas the former one was given in terms of kg. So this one now, we don't have any need to multiply with the speed of light at the end of the day. So we have a solution. As usual, E is delta N, and then there is no C in this case now. So we now have that, yes, we have a mass of product, mass of reactant minus mass of the product, mass of the product. Now, this is the reactant. The reactant is deuterium and tritium. So we now have that E is, we put the masses straight, which is for deuterium, we have 3.01605 U plus deuterium with tritium. Sorry, this is a tritium. Was 2.01410 U. We put it in brackets minus this, which is a helium. Helium is 4.00260 U plus neutron. Neutron is 1.00. So I'll write it because to not enter. I'll write it under this. 1.00867 U. Okay. If we add these two, it will now give us 3.01605 plus 2.01410 U. Everything here was 5.03015 U minus, I will add these two. If you add these two, it will give us 4.00260 U plus 1.00867. If you add the two, these two will give us 5.01127. Remember, this is E. So E is equal to, at this point, U is here. At this point, you subtract. If you subtract this from this, we will now have 5.03015 minus 5.01127 U. At the end of the day, we have that E is 0.01888 U. If you have this type of question, especially the OBJ, look out for this. If the answer is not in atomic mass units, now you now come down. At this point, you put the value of U. From here, they give us U. They say U is 931 MeV. Now, this M means mega electron volts. Mega electron volts. Mega means million. 10 raised to the power 6. So this one is 10 raised to the power 6. This one given to us here. We now have 0.01888 times U. 931 mega. That mega means times 10 raised to the power 6. Times 1 electron volt, which is 1.67 times 10 raised to the power minus 19. As usual, multiply the basis first and then add the index number. If we multiply the basis, we now say 0.01888 times 931 times 167. So if we do that, we have that E is equal to 29.35406 times 10 raised to the power. At this point now, 6 minus 19. 6 minus 19 will give us minus 13. Right, since it's minus 13, we cannot stop here because this is not yet a standard form. We put it in standard form by shifting these points here, and if we shift this here, this one will reduce, which will give us 2.93546 times 10 raised to power minus 12 joules. And this is the final answer. Between this and the former, see how it's going. If you are given the value of C, please make use of C. But if you are not given the value of C, both of them are the same thing. Now we'll take the last question. These three, the third question, which is the final question, says the radioactive nuclei will have polonium 21084 emits an alpha particle to produce lead 20682. Calculate the energy in Myfeel. This one now says a mega electron volt released in each disintegration. We have the masses of polonium, lead, helium, and the mass number given and of one atomic mass unit given to us in Myfeel. So all we need to do is the first one represents the equation. If it is given like this, the first is to represent the equation. So if we represent this equation, we now have that polonium 21084, they said, emits an alpha particle. And of course, since it emits an alpha particle, we don't need to add again. Just use this. Because this thing was not, it was not bombarded. So we have lead 20682 plus alpha particle 42, and then that of energy. This is the equation given to us. So in other words, this one we just have this is equal to, this is the reactant, just a single element reactant. The product is these two. So we now have that E is equal to mass of reactant minus mass of products, which will give us, the reactant is this. So E will give us mass of the reactant, which is 209.936730 U minus, we have this other two, 205 plus 205.92992942 U plus, I will write this one down. Down here, I will now have like 4.001504 U. At the end of the day, I will still have this one, I'll bring this one down because it's only this value. 9.936730 minus, I will add these two. So if we add 205.92942 plus 4.001504. So at the end of the day, this side will give us 209.930924. E will give us, remember there is U here, this minus that will give us 209.936730 minus 209.930924. Well, now that E is 0. In fact, to give us 5.00. Let me write it as it is here. It most likely, some calculator will give it to you in standard form, some will give it in ordinary form. I'll give it to us in ordinary form. 0.005806 U. At this point, put the value of U. Remember, U given to us just 931. So we now have E is equal to 0.005806 times 931 MeV. So which will now give us, at the end of the day, we now have 5.405 mega electron volt. So this is the answer in mega electron volts. But if they say in joules, you put the value of mega, which is 10 raised to the 6, and then put the value of electron volt, and then whatever value you get is in joules. At this point now, what you have is mega electron volt, and this is our final answer, and this is where we bring the lesson to an end. Thank you for being there with me. Please, if this lesson was helpful to you, give it a thumbs up, like this page, and then share with your friends. If you have not subscribed, please do well to subscribe to this channel. See you in my next